Hello, my name is James Case, and I am the Chief Scientific Officer at Cardiovascular Imaging Technologies. This tutorial is designed to give you an understanding of how ImagenSPECT works and to improve image quality and enable half-time, half-dose imaging in SPECT. Since the early 2000s, there has been a push to reduce patient dose and improve laboratory efficiency while simultaneously improving image quality. With the rise of competitive technologies such as PET and X-ray computed tomography, SPECT has had to address several concerns. First, the typical patient dosages are 11 millisieverts or higher. This dose is almost 3 times the dose of a myocardial perfusion PET study. In addition, scanning times are 15 to 30 minutes and requiring up to 2 hours of patient time to complete a study. Because of this, several new technologies, such as new camera designs and collimators, have been examined to improve system sensitivity and thereby reduce dose and improve image resolution. In addition, software solutions have been investigated to provide an upgrade path for those centers that choose to use conventional SPECT system designs. In 2016, Cardiovascular Imaging Technologies introduced a software solution for half-time, half-dose imaging on conventional nuclear medicine systems. The ImagenSPECT solution runs on a customer's own PC. This allows the user to pick the hardware platform that best works for them and meet all of their in-house system security needs. ImagenSPECT is compatible with most DICOM-based acquisition systems, and in many cases replaces the original processing workstation completely. ImagenSPECT is also compatible with certain proprietary data formats, such as the Pegasus format. ImagenSPECT offers a full reconstruction options, such as filtered back projection, standard 2D OSEM iterative reconstruction, and 3D OSEM half-time, half-dose reconstruction. It also includes a quality control environment for reviewing the rotating images, setting the limits of reconstruction, cine rate control, and motion-corrected, uncorrected toggling. ImagenSPECT also includes 3 different automatic motion correction algorithms optimized for different patient motion situations. Following reconstruction, ImagenSPECT can export the reconstructed volumes to your review environment or to a Cedars Cardiac Suite or Emory Toolbox environment provided by CVIT. The resolution of SPECT imaging systems is dependent on the collimator. All SPECT collimators lose resolution as a function of distance between the camera and the object that it is imaging. Resolution recovery attempts to model this distant-dependent blur and restore the resolution that has been lost. This de-blurring of the image has the effect of concentrating the reconstructed counts into a smaller area, thereby increasing the signal from that pixel. One of the limitations of these methods is that they can also amplify the noise in the reconstructed image. In order to achieve the enhancement of the reconstructed signal, an accurate model for the blur and a model for controlling the noise is needed during the reconstruction. Most half-time, half-dose software programs available on the market today rely on an iterative reconstruction algorithm, like the ordered subset expectation maximization algorithm, to integrate the blurring model for the collimator into the reconstruction. Iterative reconstructions use a stepwise algorithm for comparing the actual projection data with a virtual representation of the data. If we imagine starting with the nth iteration of an image, we then use a model to create a fictitious set of rotating projection data sets. By comparing the real projections with the virtual projections, a corrections data set can be determined for improving the n+1 image. The better the model, collimator type, resolution, scatter, and attenuation, the better the algorithm can recreate the source tracer distribution. In standard OSEM reconstruction, the image is on the left, the model only includes the radon transform. This transform assumes all of the counts originate along a straight line projecting from the detector face. Though the images improve as the number of iterations increases, these algorithms typically reach a point where no more improvements in resolution are possible, and then they amplify the noise. ImagenSPECT half-time, half-dose iterative reconstruction uses both a model for the noise and the blur of the collimator. This allows the iterative reconstruction to continue improving the resolution without amplifying the noise beyond the limits of a conventional 2D reconstruction. The result of ImagenSPECT half-time, half-dose reconstruction is superior image quality using very low dosages. This image is a comparison of a conventional filtered back projection reconstruction compared with the same dataset reconstructed with ImagenSPECT half-time, half-dose. The half-time, half-dose algorithm can change an image set that would be normally non-diagnostic into a high-quality, usable image. As with all resolution recovery techniques, high-quality data is needed to avoid amplification of the image artifacts. In particular, patient motion can represent a significant challenge for these high-resolution reconstruction techniques. Raw data should always be inspected for patient motion, and vertical and lateral motion should be corrected when it is present. There are several options available for nuclear cardiology laboratories that choose to use conventional SPECT imaging instrumentation. In this illustration, ImagenSPECT is compared with another workstation solution for performing half-time imaging in a uniform cardiac phantom. ImagenSPECT is optimized to provide the most accurate representation of the source data. This requires upfront correction of any motion artifact and accurate modeling of the noise and blur image to achieve true image improvement. In summary, half-time, half-dose imaging with ImagenSPECT is adaptable to most of the conventional geometry SPECT systems on the market today. It uses a resolution recovery technique to concentrate the same counts into a smaller space, thereby increasing the relative signal to noise. It also employs an iterative noise model for controlling the noise amplification at each step of the reconstruction process. As with any high-resolution reconstruction technique, the input data must be of high quality. That includes anti-aliasing correction and motion correction. When all of this is combined, the result is a final reconstruction that preserves resolution without introducing any new artifacts. For an online demonstration of ImagenSPECT, please visit www.cvit.com or send an email to imagen@cvit.com. Thank you for watching this tutorial, and please subscribe below.